Rates of change. Slope of a tangent can be viewed as a rate of change. Since slope is the ratio of the change in y over the change in x, that is, slope is delta y over delta x, we say that the slope is the rate of change of y with respect to x, right? So how is the y value changing with respect to x? In this investigation, we will look at other rates of change, starting with velocity. So suppose Sam drove to Edmonton, a distance of 300 kilometers in 3 hours. We can use the following formula to determine Sam's average velocity. So I think you should change distance to displacement, right? Like, to be technically correct. Anybody doing physics? I mean, velocity is a vector quantity and distance is a scalar, so it should be displacement. Anyway, you should say like 300 kilometers north and all of that good. But so just forgive us any inconsistencies in stuff. What? Oh, so that's the end of last period now, right? Because it was supposed to be 209, but they couldn't unring that first bell. So maybe we should pause. Well, heck with it. Okay. So average velocity is the change in distance, displacement, over the change in time, which is delta s. Although you use s for that's distance and d is I don't know. So what is his change in displacement? Well, it's 300 kilometers, and the change in time is 3 hours. And 300 divided by 3 is 100. Right. 100 kilometers per hour. North. Displacement. Alright, I'll leave this up for a second. Sam's average velocity was 100 kilometers an hour. So does this mean Sam was consistently traveling at 100 kilometers an hour? Likely not. Possible, but likely no. Your instantaneous velocity, your velocity at any moment in time is likely to change, but averaged over the time interval of 3 hours, we come up with the average velocity. So how do we determine his velocity at a given instant in time rather than over an interval of time? Now you hit him with the radar gun and you'll know the instantaneous velocity, which hopefully is less. Does this sound similar to the problem of determining the slope of a tangent when we know only one point rather than an interval of change in x? And if it doesn't, it should. So, example 1. The displacement of an object in meters is given by s equals f of t, which is 5t squared, where t is the time in seconds. Complete the following table of values. Okay, so then we do that, right? 5 times 1 squared, 2 squared 4, 3 squared 9, 4 squared 16. I think that's correct values of s when t is 1, 2, 3, and 4. And this is in seconds, right? So we've got meters per second. Complete the following statement to determine the average velocity from t equals 1 to t equals 4. Right? So what would you be doing? You could graph this, and then you would have your 2 points. Right? So you kind of graph this and had your 2 points. And you were basically figuring out the slope of the secant line between those 2 points, right? Because the displacement time curve, if you're moving at an increasing rate of speed, would look like this. Right, so you're working out that slope, right? So slope, well, the change in displacement over the change in time. So f4, which is 80, minus f of 1, which is 5, over 4 minus 1, which is 3. So that's 75 over 3, or 25 meters per second, and give it as a velocity. There should be a direction associated with it, but I didn't make up the sheet. So. Determine the average velocity from t equals 1 to t equals 3. Okay, so we're going to do the exact same thing. We're actually going to show the exact same work. So you can do that, right? Just show the exact same work. What's the difference? This will be f of 3. This will be a 3. Okay. Now we want to do this, right? We want to show this because it actually leads somewhere, right? So we're going to do the same thing. Delta S over delta T is f of 3. I mean, yeah, we could just look at that and just say, hey, it's just whatever, right? But we want to show the work. And hopefully in your assignment you've shown enough detail, right? You don't just kind of leave out. Like, I get confused easily, so I need to see a reasonable amount of detail. So f of 3 is 45 minus 5 over 2, which is 40 over 2, which is 20 meters per second. So the average velocity from time 1 to time 3 is 20 meters per second. Determine a simplified expression for the average velocity from t equals 1 to t equals 1 plus h. Okay? We're going to do the same thing, right? It's a little bit more general, though. So change in displacement over change in time, delta s over delta t. So f of 1 plus h minus f of 1 over 1 plus h minus 1. Okay, I kind of like to bracket that just to sort of show that it's a separate, that's the 1 plus h, right? Okay, did we get a definition for f? We did 5t squared, right? 5t squared. So we've got to go 5 times 1 plus h squared minus 5 times 1 squared, right? So t, f of t, right? F of 1 plus h, so 5 times 1 plus h, quantity squared, minus 5 times 1 squared over h. And we can do a little math, right? So we've got to expand this and blah, blah, blah. So let's do it. 1 plus 2h plus h squared minus 5 and right? You got 5 minus 5, so that's all gone. Oh, look, they've got an h there, so h bracket. And we'll extend the ph because we got a room there. Okay, so the average velocity from time of 1 second to time of 1 plus h seconds can be expressed as 10 plus 5h. Right, so h is just the change in time, right? So I think I graphed this. There's 5t squared, and there's 1 second, and then I can't draw it. And then, you know, h, if h is 2 seconds, you're going from 1 to 3 seconds, and so on. What's that? It's the slope of the secant line. And then we ask, well, what's the instantaneous velocity at time 1? So we got to start bringing that down. We're going to bring h down to 0, right? Just like we did yesterday. So it'll be the instantaneous velocity. I should be able to spell it because it's right there in front of me. Instantaneous velocity is equal to the limit as h approaches 0 of 10 plus 5h, which is equal to, anyone? 10, right? Yeah, because we can throw 0, right? You got rid of it on the bottom there. That's the whole idea with the limits is, we got something that's 0 down here, so we need to eventually end up canceling. We get 10. 10 what? What's velocity measured in meters per second? And really, truly, there should be a direction, right? Because that's a vector quantity, and it has, you know. So I really just know that it bothers me a little, but not enough to change anything.
So we don't have to do that on the test.
Well, yeah, you know, we'll play fast and loose with physics and vectors and stuff, but you know, when you start doing this for real in physics, like which wouldn't happen to university because you wouldn't use any calculus in physics until then, you know, then you'll be much more careful. You also worry about significant digits too, right? We don't do sig digs, so or sig figs. Okay, so in general, if an object moves, this is kind of where this differential calculus started, right? It was back in the 1600s they were trying to figure out, well, so what is the velocity at, you know, we have a curve, we can measure displacement in time, we get this curve. How fast is this thing going at this point in time, this instant in time, how fast is it going? So they had to figure this out, right? This was the basis of this. So in general, if an object moves according to an equation, s equals f of t, where s is the displacement, which remember displacement is a directed distance, we just haven't directed it at all, from the original position at time t, then we could just call it forward though, right? It's going forward. Then s equals f of t is called the wait, I'll fill this in for you. It's called the position function, right? It's the position with respect to time. The average velocity from time t equals a to t equals a plus h is given by change in position over change in time. Change in position is f of a plus h minus f of a, right? Just the difference in the y values. Basically the slope of the secant line which passes through the 2 points on the curve, right? So you know, there's the curve, and I can't draw points, but if I could, then it's the slope of the secant line passing through those 2 points, right? And then you've got this point here, which is a plus h and f of a plus h, and you got this point here, which is a and f of a, and then this, you know, what we did yesterday. Okay, I mean, you've seen that. So the average velocity is f of a plus h minus f of a over h, right? Because it's a plus h minus a, so the change in time is h, right? We've moved from this time to this time on the graph. The instantaneous velocity at that instant in time, right? So it's got to be a point in time, about a one-time value, excuse me, which is denoted by v of a, is the blank of the average velocity as h approaches 0. So if h is approaching 0, then it's the what? It's the limit. Right, anything back there, so all we're doing is taking that secant and just getting closer, closer, closer until it becomes the same as the slope of the tangent. And is given by v of a equals the limit as delta t approaches 0 of delta s over delta t, which is equal to the limit as h approaches 0 of basically the velocity, right, which is f of a plus h minus f of a over h. Or sorry, the limit of the average velocity as h approaches 0, as we bring that closer. So it means the velocity at time t equals a is equal to the slope of the tangent to the position function, right? S equals f of t, called the position function, at time t equals a. Did you do any of this in like junior high science or grade 10 or anything where you drew the curve and then you tried, just eyeballed a tangent line? Like,
oh yeah.
yeah? And then measured the slope, so you're trying to figure out, right? Well, so that's where that came from, right? So you look back and think about, oh, hey, because I remember doing this in like grade 9 science where we would draw the curve, position versus time, and then we'd say, well, how fast is it going here? Well, we're drawing a tangent line, right? Because that's the instantaneous velocity at that moment in time. Okay, the displacement in meters of an object is given by s equals t squared plus 2t, where t is the time in seconds. Determine the average velocity from time 3 to time 5. Okay, so what are we going to start with? Average velocity is delta S over delta T. Okay, which is equal to F of, or S, sorry. What do we got here? S of 5 minus S of 3 over 5 minus 3. Okay, which we can now fill in, right? So we want basically the y value at 5 seconds. How far have you gone after 5? How far did you go after 3? How far did you go in that time interval? And this was the time interval, right? The 5 minus 3 in that 2 seconds. How far did you go? Okay, so we've got 5 squared plus 2 times 5 minus 3 squared plus 2 times 3 over 2. So we just write, what do we got? 25, this will be 35, and 9 plus 6, that's 15. Okay, so 20 over 2, which is 10 meters per second. Okay, so the average velocity in that time interval is we covered 20 meters, right? We went from 15-meter position of 15 meters to a position of 35 meters, so we went 20 meters in a time of 2 seconds, which gives us 10 meters per second. What was the instantaneous velocity at 3 seconds? So instantaneous velocity, v of 3, right, the velocity at 3 seconds, is the limit as h approaches 0 of s of 3 plus h minus s of 3 over 3 plus h minus 3, right, or just h, right? Okay. So now we work these out, right? It's a more general formula. We're not putting 5 in for t, we're putting 3 plus h in, so we've got to square that and add 2 times t, whatever. So it's the limit as h approaches 0 of, okay, so what do we got? T, so it'll be 3 plus h squared plus 2 times 3 plus h minus, let's bracket that, s of 3, which just that, okay, so minus 3 squared plus 2 times 3 over, and that's just h. And I have to extend this again. So hopefully this h will go away. We know. What do we got? 9 plus 6h plus h squared plus 6 plus 2h. What's this? What is that, 15? Minus 15. So 9 plus 6 minus 15. 9 plus 6 is 15, right? So 9 plus 6 minus 15. Gone. All right, what do we got? H squared plus 8h. Okay, so let's call that h bracket h plus 8 over h. Okay, and this came from this, right? So we got h squared plus 8h. That's what's left up here. And we're going to write it as h times h plus 8, so we can cross these guys off, right? And so that's equal to 8. This is where limit as h approaches 0 goes away, right? And on Monday, that's where it should go away on your test. Only here. Don't drop it up here, right? I mean, I've seen that before. So we want to make sure that we keep this until we're ready to substitute in 0. You can't do that until, right? You can't do that here. And that's equal to 8 meters per second. So the instantaneous velocity at 3 seconds is 8 meters per second. Okay, that's how fast it's going at 3. We could do the same thing for 4 and 5 and 6, right? For any number by substituting in, right? 4, 5, 6, so on. Question? Good. Okay, we're almost done. Well, you can tell that we're on the back. We're on the last page. In general, if y is a function of x, that is y equals f of x, then the average rate of change of y with respect to x at x equals a is given by delta y over delta x is equal to f of a plus h minus f of a over a plus h minus a. And the instantaneous rate of change, so that's the average, right? It's just taking the 2 points on the graph. So what's the difference in the y's? What's the difference in the x's? Instantaneous rate is the limit as this value approaches 0, which is f of a plus h minus f of a over h. So let's do example 3, last example. A spherical balloon is being inflated. Determine the rate of change of surface area with respect to time when the radius is 8 centimeters. Right? So if you think about inflating a balloon, its area is going to change, right? It won't be changing at a constant rate. It's ever increasing. As it gets bigger and you blow it up more, then its surface area increases more. Okay? And we have a rate of change that we're looking at. Rate of change when the radius is 8 centimeters. Right? You'll have a different rate of change when it's 4 centimeters. You'll have a different rate of change when it's 2 centimeters. I want to make that SA. S, come on, surface area, whatever. But so the area of a sphere is 4 pi r squared. All right, so rate of change, well, it's a limit as h approaches 0 of f of a plus h minus f of a over h. So that's just general formula, right? I always like to write formulas down. Okay, then we're going to substitute in. So we have a particular, we'll call it S, right? Because SA doesn't fit, so we'll go with S. And actually, that's not equal to, it's more. Leads to, the limit as S approaches A of S of 8 plus H minus S of 8 over H. Okay, and then we'll fill that in. So we know what the function S says to do, right? It says take that, that's your radius, so it becomes 4 pi. So that's equal to the limit as h approaches 0 of 4 pi 8 plus h squared. Okay, that's this guy. Minus 4 pi 8 squared over h.
Why is it 4 pi? 4 pi.
It's 4 pi r squared. So the 8 plus h is going to be the first r, right? So, I mean, think of it as S of r, right? Surface area as a function of radius. So the surface area is changing. Surface area is a function of the radius as the radius changes 4 pi r squared. Okay, so we're going S of 8 plus h. Okay, now, first thing we do is notice, hey, there's 4 pi's on both of those guys, so let's factor out the 4 pi's. So limit as h approaches 0, 4 pi. Okay, and then 8 plus h squared minus 8 squared over h, right? So get rid of the 4 pi's. You don't want to have, we don't want 4 pi's all over the place. Okay, so 4 pi, and what do we got? 64 plus 16h plus h squared minus 64 over h. And you notice you got an h in common here, right? So it's like 4 pi. So let's throw in one more line, can't hurt. So 4 pi h, 16 plus h over h. So all I've done there is just factor the h out of 16h plus h squared, okay, so that we can then cancel the h's. And now we get to draw limit as h approaches 0, and what do we get to write?
64 pi.
64 pi, thank you. Okay. 64 pi, some units. What units was this in? Centimeters squared per second. Right, it's a change in area. The area, because the thing is measured in centimeters, will be centimeters squared, and it's the rate of change, so centimeters squared per second. Where is that? It says here, centimeters squared per centimeter. Oh, sorry, centimeters squared per centimeter. My bad, it's not per second, it's per centimeter because it's the rate, we don't have seconds in there, right? It's radius. Radius is changing in centimeters, area is changing in centimeters squared, so it's area changing with respect to radius. So it's changing at 64 pi centimeters squared per centimeter at 8 seconds, right? If you want 4 seconds, you put a 4 in, 5 seconds, and so on.
What is that?
Okay. Done.